For the last few months, every forecast, every headline, every video about the coming winter has been about one ocean. The Pacific is heating up, a super El Niño is building, and by December it will be one of the strongest on record. While everybody W is watching that, the Atlantic did something almost nobody noticed. In the middle of July, a patch of ocean along the equator, west of Africa, started going cold. Hot, slightly cold. Cold enough that within days it showed up as a blue scar on the global temperature maps, running from the African Sea Oast out toward Brazil, while everything around it stayed warm. It's now sitting somewhere between 2 and 5 degrees Fahrenheit below normal, and if it holds through the season, it will be only the 6th event of its kind in more than 40 years of records. So we now have 2 of the biggest ocean patterns on the planet running at once, in opposite directions, in 2 different oceans. One record warm. See cold event in perspective. Researchers have been tracking sea surface temperatures across this stretch of ocean with reasonably reliable instrumentation for a little over 4 decades now, and in all that time, an event of this magnitude has only shown up a handful of times. That's not a pattern that comes around every few years in any predictable way. It's rare enough that most people working in seasonal forecasting have never had to account for one landing on top of a major Pacific event before, which is part of why the combination caught so many forecasters off guard this summer. And here's the part that makes this worth your attention. Your instinct is that 2 opposite anomalies should cancel each other out. Heat on one side, cold on the other. The atmosphere splits the E difference. They do not cancel, they add. Both of them push the atmosphere in exactly the same direction, and the result is a single unusual setup sitting over the Atlantic right now, one that has already forced forecasters to tear up their hurricane predictions for the year and start again. This is what that setup is, why 2 opposites push the same way, and what it means for the next 6 months. First, the correction that matters, because the name people are using for this is wrong, and it will confuse everything that follows. La Niña, properly speaking, lives in the Pacific. It's the cold phase of the same cycle that produces El Niño, and by definition, you cannot have both at once in the same ocean. When one is running, the other is not. What's happening in the Atlantic is a different pattern node. Zonal means along lines of latitude, which is exactly what it looks like on a map. A band running east to west along the equator. Like the Pacific cycle, it swings between a warm phase and a cold phase every few years, and the cold phase gets called the Atlantic Niña. So this isn't El Niño and La Niña at the same time in the strict sense. It's El Niño in the Pacific, and its Atlantic cousin running cold at the same time. Which is arguably stranger because the Atlantic version IS far less studied, far less predictable, and almost nobody outside the field knows it exists. That lack of attention isn't because it doesn't matter, it's because the Atlantic is the ocean our models are worst at. Every major climate model shares the same error there, and it isn't a small one. They run the tropical Atlantic too warm. Systematically, persistently, across every generation of models, including the current one. In seasonal forecast experiments, the error shows up within the first month and reaches 80% of IT's full size within 6. And because the bias suppresses exactly the cold tongue that defines this pattern, the models are demonstrably bad at reproducing the thing we're about to spend the next several minutes discussing. We're watching a rare event in the one ocean basin where the tools are known to be least reliable. It's worth sitting with why that bias exists, because it isn't simply a case of scientists overlooking something obvious. The tropical Atlantic is a narrow basis compared to the Pacific, hemmed in on both sides by continents, which changes how heat and moisture move through it and makes the physics genuinely harder to represent in a global model built to handle every ocean basin on Earth with the same set of equations. A model tuned to perform well in the vast, open Pacific doesn't automatically perform equally well in a tighter, more continentally constrained basin like the Atlantic, and that mismatch shows up as exactly this kind of persistent warm bias. Researchers have chased this problem for decades, testing different ways of representing cloud cover, wind stress, and ocean mixing near the equator, and the bias has proven stubborn across nearly every approach tried so far. It isn't for lack of effort. It's a genuinely hard modeling problem, sitting in the one basin where getting it wrong carries some of the highest stakes on the planet. There's also a timing problem layered on top of the physics problem. A Pacific El Niño typically takes well over a year to build from its first faint signals through to a confirmed strong event, which gives forecasters a long runway to detect it, T-rack it, and issue increasingly confident warnings as the season approaches. The Atlantic zonal mode doesn't offer that kind of runway. It can develop and peak within a single summer, which means the window between the first T of a signal in the data, and the point where it's already reshaping the monsoon or the hurricane season can be a matter of weeks, not months. Combine a model that's already biased warm with a pattern that moves this fast, and you get a basin where confirmation regularly arrives close to, or even after, the point where the forecast would have been most useful to the people depending on it. So how does a stretch of tropical ocean, sitting on the equator under the strongest sunlight on the planet, get colder than it should be? It doesn't lose heat. It gets replaced. The eastern equatorial Atlantic already does this every year, and the seasonal cycle there is counterintuitive. The warmest water of the year shows up in spring. The coldest arrives in July and August in the Medinlodapas, DL of northern summer, when the surface drops below 77 degrees Fahrenheit, 25 degrees Celsius. The ocean is at its coldest when the sun is at its strongest. The reason is wind. Along the equator, the trade winds blow from the southeast, and because of the way the Earth rotates, a wind blowing along the equator doesn't simply push the surface water forward. It pushes it sideways, away from the equator, in both directions at once. The surface layer peels apart down the middle. Water has to come from somewhere to fill the gap, so it comes up. Cold water from a fill. At 100 feet down, water that's been sitting in the dark rises to take the place of the warm surface layer that's been dragged away. That's upwelling, and it's one of the most important processes in the ocean because it's also what brings nutrients up and makes the equatorial Atlantic productive enough to feed the fisheries of the entire Gulf of Guinea. That fisheries connection is worth pausing on because it's a preview of the same pattern that shows up later with the Sahel's rainfall. Upwelling doesn't just cool the surface, it also drags nutrient-rich water up from the depths, and those nutrients are what fuel the plankton at the base of the food chain that fishing communities along the West African coast rely on. A stronger than usual upwelling season, driven by these same strengthened trade winds, can mean a genuinely better year for coastal fisheries, even while it's creating a colder ocean surface that suppresses hurricane formation thousands of miles away and disrupts monsoon rainfall further inland. The same physical process is delivering a benefit to one group of people and a hardship to another, depending entirely on where they happen to sit relative to that band of cold water. That's not unusual for large-scale ocean patterns. It's simply rarely discussed alongside the hurricane angle, because the fishery's impact doesn't show up in a satellite loop the way a tropical storm does. This year, the winds strengthened, the peeling got stronger, and more cold water came up than usual. That's the entire mechanism. No mystery, no exotic physics, just wind dragging a surface lay, R aside, and the deep ocean rising to fill the hole. What makes it interesting isn't how it happens, it's what happens next, in the air above it, which brings us to the thing that shouldn't work. It's worth pausing on just how ordinary the ingredient here really is, because that's part of what makes this event easy to miss until it's already well underway. Trade winds strengthening and weakening over the tropical Atlantic isn't itself unusual. It happens constantly, tied to all sorts of shorter-term atmospheric fluctuations that come and go within a season and rarely make the news. What makes this year different isn't a new physical process nobody has seen before. It's the combination of an ordinary strengthening of the trade winds landing at the same moment as an extraordinary event unfolding on the other side of the planet. Neither half of that combination required anything exotic. The Atlantic just needed its usual summer wind pattern to run a bit. Just needed its El Nino cycle to keep doing what El Nino cycles do when they build toward a strong or super strong event. Two unremarkable ingredients, arriving together, produced a genuinely remarkable outcome. One ocean is unusually warm. The other is unusually cold. Every instinct says they fight each other and the atmosphere ends up somewhere in the middle. It doesn't. They pull in the same direction, and the reason is a piece of atmospheric plumbing most people have never had explained to them. Here's the thing to hold on to. The atmosphere doesn't care whether water is warm or cold in the abstract. It cares about where air rises and where air sinks. Warm ocean makes air rise, the water evaporates, the moist air climbs, it cools, the moisture condenses into towering clouds, and you get thunderstorms. Cold ocean does the reverse. Less evaporation, less rising air, and the column above it becomes stable and heavy. And crucially, air that goes up somewhere has to come down somewhere else. The atmosphere is a closed system. Every region of rising air is paired with regions of sinking air, and if you move the rising, you move the sinking with it. Now apply that to what's happening. El Nino has taken an enormous volume of rising air and thunderstorm activity and dragged it east into the central Pacific, out over open water where it doesn't normally sit. That's what an El Nino does. It relocates the engine, and the compensating sinking air lands to the west and east of it, including over the tropical Atlantic. At the same time, the Atlantic has gone cold on its own account, which suppresses rising air locally for its own separate reason. So the Atlantic is being pressed down from two directions at once. Once remotely, by an ocean thousands of miles away rearranging the global circulation, and once locally by its own surface going cold. Two completely independent mechanisms, arriving at the same place, doing the same thing. The result is what forecasters who first flagged this pattern have called an atmospheric shield. That's not an official meteorological term, but it describes the setup accurately. Higher pressure, sinking air, stronger wind shear aloft, and less rainfall across the exact stretch of ocean where Atlantic hurricanes are supposed to be born. There's a stretch of the Atlantic that forecasters call the main development region. It runs from the west coast of Africa across to the Caribbean in a belt along the tropics, and it's where the majority of the season's serious hurricanes are born. The process starts over land. Disturbances roll the African continent every few days in summer, called African easterly waves, and they drift out over the ocean. Most of them do nothing. A few find warm water, moist rising air, and light winds aloft, and they organize, spin up, and become the storms that make landfall weeks later. That nursery needs three things: warm surface water to supply energy, rising moist air to build the storm, and calm winds aloft so the growing structure doesn't get sheared apart before it stabilizes. The setup we've just described removes all three at once. The water in the eastern part of the region is colder, the sinking. Air suppresses the rising motion. And the wind shear that comes with a strong El Nino tears at anything that does start to organize. This is why the seasonal forecasts have been revised downward, and it's why NOAA has said the two patterns are working in the same direction, both acting to reduce Atlantic hurricane activity this year. It's worth being precise about what that does and doesn't mean, because this is where these stories usually go wrong. A suppressed season is not a canceled season. It takes one storm finding a gap in the shield at the right moment, over water that's still historically warm closer to the coastate, to make the year memorable for whoever it hits. Quiet seasons have produced catastrophic landfalls before. Fewer storms is a statement about the average, and nobody experiences the average. This distinction matters more than it might sound like on first pass, because forecast headlines and lived experience measure two completely different things. A seasonal outlook is built from historical relationships between ocean states, and storm counts, averaged across dozens of past seasons that shared similar conditions. That's a statement about the population of possible seasons, not a guarantee about this specific one. Somewhere inside that quiet average, there's still room for a single storm to intensify rapidly right by E for landfall, catching a coastline that let its guard down because every headline all summer said this would be an easy year. The seasonal forecast and the emergency preparedness message are not the same message, and treating a below normal outlook as permission to skip storm prep is exactly the mistake this kind of coverage tends to encourage, even when nobody intends it to. Almost every story about this pattern stops at hurricanes, because hurricanes are what the American audience is watching for. But the Atlantic zonal mode has a much larger and much less discussed consequence, and it lands on the other side of the ocean. The same band of water that Saint went cold sits directly beneath the engine of the West African monsoon. The temperature of that surface controls how much moisture rises off it, and that moisture is what gets carried inland to fall as rain over the Sahel, the belt of semi-arid land running across the continent below the Sahara. For the people living there, yes, the difference between a warm phase and a cold phase of this pattern isn't a curiosity. It's the difference between a harvest and a failed one, across a region where hundreds of millions of people depend on rain that arrives in a single short season and doesn't come back if it fails. It helps to be specific about how thin that margin actually is. The Sahel's growing season typically runs from June through September, a window of a few months in which farmers across countries like Mauritania, Senegal, Mali, Burkina Faso, Niger, and Chad need to receive nearly all of their year's rainfall in order to grow the staple crops that feed their communities. There's no equivalent of a second planting later in the year if the first one fails, and there's no large-scale irrigation infrastructure across ENSO, a T of this region capable of making up the difference when the rains fall short. A shift of even a few weeks in when the rains arrive, or a modest reduction in total rainfall, can be the difference between a normal harvest and a shortfall, serious enough to trigger food insecurity across an entire country. That's the scale of consequence riding on a patch of ocean temperature that most weather coverage never mentions at all. This is the reason the Atlantic zonal mode has been studied at all, and it's also the reason the model bias we mentioned earlier is more than an academic complaint. The models are worst in the exact basin where the forecast matters most to the people with the least ability to absorb a bad year. A quieter hurricane season in the Atlantic is good news for the American coast. It is not automatically good news for everybody standing around the same ocean. So where does this leave the next 6 months? Through the rest of hurricane season, the shield holds as long as both halves of it hold. The Pacific side looks secure because El Nino is STI, RD the end of the year. The Atlantic side is the uncertain one. This kind of cold event isn't guaranteed to persist. It's faded before, and if the trade winds relax, the upwelling weakens, and the water warms back up within weeks. If that happens, one leg of the shield goes away while the El Nino leg stays in place. The shield gets weaker, not gone. Into the winter, the Pacific side takes over almost entirely. A strong El Nino reshapes the jet stream over North America, and that's a much better understood signal than anything we've talked about today. It tends to push the jet stream south, bringing wetter, stormier conditions to California, the desert Southwest, and the Gulf Coast, while pushing milder, drier weather into the northern tier of the country, the Pacific Northwest, the Northern Plains, the Great Lakes. That part of the forecast rests on decades of well-documented pattern behavior, not on the newer, harder-to-model Atlantic signal. But the thing worth taking away here isn't the forecast itself. It's the shape of what just happened. Two oceans on opposite sides of a planet, running opposite anomalies for entirely unrelated reasons, and the atmosphere between them added the two together instead of splitting. The difference. Nobody planned it, and nobody predicted the combination, because the tools we use are demonstrably weakest in one of the two basins involved. We spent this year watching one ocean very carefully. The other one changed while we weren't looking, and it turned out to matter just as much. Think about how differently this story would have been told if the Atlantic anomaly had simply gone unnoticed for another month or two, the way it very nearly did. The hurricane forecasts would have been revised downward anyway, because the Pacific's signal alone is strong enough to explain part of that shift, but the explanation offered to the public would have been incomplete. An El Nino story missing half its mechanism, and on the other side of the ocean, the people watching the Sahel's rainy season wouldn't have had any warning at all about why the rains were running short, because nobody outside a small group of SP. Actualists would have known to look for it in the first place. That's the real risk buried inside a model bias like this one. It's not just that a number comes out wrong, it's that an entire population depending on that number can go without any warning whatsoever. So the question worth sitting with is this one. Should a forecast that says fewer storms make you feel safer, or is a quiet season actually the more dangerous kind? Precisely because it's the one where people stop preparing, right up until the one storm that matters finds the one gap left in the shield. There's no clean answer to that, and anyone who gives you one with total confidence is telling you more about their own certainty than about the atmosphere. What's true is that average and individual outcomes are two different things, and a forecast built on averages will always undersell the risk to whoever ends up standing in the path of the exception. What's also true is that this entire event, record warmth in one ocean, rare cold in another, both pushing the same direction, both converging on one stretch of tropical Atlantic that most people I've never heard of, happened almost entirely outside public attention, while a much louder story about a single ocean dominated the conversation. That's not a criticism of anyone paying attention to the Pacific. The Pacific signal is real, well, understood, and genuinely historic in its own right. It's simply a reminder that the planet doesn't organize itself around whichever story is getting the most coverage in a given month. It runs multiple systems, on multiple timescales and multiple ocean basins all at once, and some of those systems are far easier for us to see coming than others. There's also a broader lesson here about how forecasting coverage tends to work in general well beyond this particular event. The story that gets told first is usually the one with the biggest, cleanest sigh-long buildup, its well-documented mechanics, and its familiar effects on North American weather. That story is easy to tell because the data supporting it is unambiguous and the pattern has been studied for decades. A quieter story, the one developing in a basin our models struggle with, in a pattern most people have never heard of, tends to arrive late to the conversation, if it arrives at all. That's not because anyone is deliberately ignoring it. It's simply harder to tell a confident story about something the tools themselves are known to get wrong. But confidence in the telling and importance of the underlying event are two completely different things. And this year is a fairly clean example of a quieter signal turning out to matter just as much as the loud one sitting right next to it. The Pacific El Nino will keep strengthening through the fall, and its effects on winter weather across North America are about as well established as seasonal forecasting gets. The Atlantic Niña is the wild card. It could hold through the rest of hurricane season and keep the shield intact, or it could fade within weeks if the trade wind ease off, in which case the picture changes again. Either way, the rains over the Sahel this year are already being shaped by what happened in that patch of ocean back in July, whether or not the rest of the world was watching when it happened. That's really what this story comes down to. Not a single forecast number, but a reminder that two oceans, doing opposite things for entirely separate reasons, don't have to cancel each other out just because our intuition says they should. Sometimes they add. And when they do, the effects show up in places most people never think to look. In a quieter hurricane season on one side of the ocean, and in a harvest that either comes in or doesn't on the other.